So let's move on. So we're talking about Lenz's law. We had a pre-class video and some questions, so I wanted to go through and address those here. But here's our definition of Lenz's law. So there's an induced current. Excuse me a second. So there's an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. The direction of the induced current is such that the induced magnetic field opposes the change in the flux. So you guys had a few questions regarding this last night, so I wanted to go over them and see what we thought. And so here is my strategy. So like in the video, I talked a little bit about the strategy. So the first thing is you find the direction of the magnetic flux that's penetrating the coil that you're dealing with. Okay, so sometimes that's easy, like the problem gives it to you. Sometimes you've got to use right-hand rules to figure out what magnetic field you're dealing with. And then the key, all right, is determine whether the flux that penetrates the coil is increasing or decreasing. Okay, if it's increasing, then your induced magnetic field opposes the magnetic flux. If it's decreasing, the induced magnetic field is aligned with the magnetic flux. And then you used your curly right-hand rule to determine the direction of the induced current. And so a question from last night, so is it more precise to say that there will be induced current if there's a change in the magnetic flux, change in the B field inside the enclosed area of the loop rather than just the entire B field? So yeah, I would agree with that. So we're looking at the flux through our loop in the particular system that we're talking about. So here's the first one we had from last night. So you guys had a chance to think about this yourselves. So let's go ahead and try this dealing with your neighbors. So we've got this setup here, similar to the setup we were dealing with last time that we thought of as we described it as motional EMF. So we got this metal bar attached to this conducting wire here. So we've got like a circuit. And it's moving this way here. So I want to know will there be an induced current in this circuit? And which way will it go if there is one? So discuss this with your neighbors and see what you think. Okay, I see a lot of good right hands out there. All right, and so the good news is I think we did pretty good on this. So I'm going to go ahead and call time. So if you didn't get something, put your answer in. Again, we're not graded on correctness or not, just whether we do it. So I do believe I agree with the majority. And so I would say counterclockwise. Anybody want to tell me what they were thinking on this one? Want to be brave and tell us what they were thinking? There's a couple ways to think about this one. Yeah. Okay, so last time when we looked at one like this, we looked at it in terms of this idea of motional EMFs. When we move that bar, you can think about the charges in that bar feeling a force from that external magnetic field they're going through. And that, if you look at do the right-hand rule on that force, it'll send everything in a counterclockwise fashion. Did anybody think about this in terms of the Lenz's law? Yeah.
The bar moves right, you allow more B fields or magnetic flux to go through.
Mm-hmm.
Counteract that, you want fields to come to constant state, and if you right-hand rule that, it goes.
Okay, great. So that's two. In this particular example, there's two ways to think about it. So for this case, it's good to have those because you can kind of check yourself. But again, so my method when I do this is I sort of say, okay, so here's my loop. I always make my loop circular for some reason, but we look at the before and the after. And so before, maybe there's 4 magnetic field lines piercing in. As that bar moves over, I'm going to add some. So maybe now there's 6 or something. So just like we were saying there, what that means then is I want to get my after to look more like the before. Okay, so nature wants to keep things the same according to nature. Lenz's law, and so that would mean my thumb is coming out. I'm making a magnetic field coming out, which would lead us to a counterclockwise current. Okay, anybody questions on that? So we had about a 70-30 on that one, which I think is pretty good for just seeing it recently. All right, and so here's your comments from last night. So I think basically the comments were just like what people were saying when we talked about them. So the correct answer is moving the rod with velocity to the right causes positive charges. So this person was using the motional EMF idea and the right-hand rule to figure out the forces on those charged particles. This person here was using the Lenz's law application. So magnetic flux increases because of increasing area, since the B field already points away from us, and we need to cancel out this increase. To do this, we need a current going counterclockwise by the right-hand rule. So most people who got it right used one of those two. Now incorrect, so here's a good thing to think about. So there is no induced current because the B field stays constant, right? So there's 2 things that are magnetic flux. It's the B field, but it's also that area, okay? And so it's how much B field lines, magnetic flux is going through your loop. And so there's other ways for that to change besides just changing the magnetic field. So you got to be careful. And then here, someone said, so the current are clockwise using the right-hand rule to check the direction of the going out field. Okay, and so this one here, I believe, was just using the magnetic field that was there. And so these are sort of the most common errors people made last night. And so again, with this is you're looking at opposing the change in the magnetic flux, which is a pretty tricky thing to get used to when you're first doing this. And so let's try another one and see how this one goes here. So you didn't have this one last night. So let's try this. At first, let's not talk to our neighbors. Let's just think about this ourselves. We'll put a vote in, and then we'll think about this afterwards, talking to our neighbors. So just sort of put in what you think. So here we have a magnetic field coming out at you. There's a loop. And what's happening here is we decrease the magnetic field. So whatever's causing it, we sort of turn that thing down or whatever it might be. So think about this here. And again, we want to try to do this one where we do it ourselves at first, and then afterwards talk to our neighbors and see if we can try to convince our neighbors about what we're thinking. Okay, so I think this is most everybody. So let's just give you a few more seconds. If you're still thinking, again, we're not judging here. Go ahead and just put in what you think. But right now, we have a balance of something like this here. And so let's see, which that's actually pretty good. So now let's do that again, talking with your neighbors, and see if you can convince your neighbors of what you're thinking here. Okay, so I think we did a good job. So looks like we pumped that number up pretty substantially. So that's nice. And I do agree with the majority there, but that's good. So it looks like we're doing well. So go ahead and, again, put an answer in here just so we get credit for it. But I think what happens with this one is this is a little bit a trickier one. So again, here's my before and after. And so, maybe there's 4 lines coming out before. So when we turn it down, maybe later on there's 3 lines going down. And so what you want to do is you want to make a magnetic field that's coming out. Again, you want to make the after, you want to try to make it look like the before. So you want to come out, which would lead us to, again, a counterclockwise current. And so some of the comments I've gotten from people about this one is I think there's a tendency to just sort of always want to oppose the magnetic field that's there. But again, you're opposing the change in the magnetic field. So you got to be careful. So that one can be a little bit tricky. Questions on that, anybody? It looks like we did pretty good on that, I think. Let's try one more. So here, we've got a current carrying wire, sort of like we would have been dealing with on the test last night, possibly, and a loop that we're moving towards that wire. So again, this is one you guys looked at last night, and so you already have looked at it. So go ahead and talk to your neighbors and see what you think on this one, and let me know what you get. So which way will current be flowing in here if there is indeed current flowing in here? Okay, we'll give a few more seconds on this, so go ahead and put your answer in if you haven't got it quite yet. So this is one, like I was talking about before, so the first step we had there was to figure out your magnetic field. Sometimes it's really easy. In this case, it takes a little bit more work. And so what we got to do is use our right-hand rule that we would have maybe used last night on the test, right? And so if I do that right-hand rule, you find that the magnetic field comes out on that side and goes in on that side, right? So we use our other curly right-hand rule. So my thumb goes with the current. It comes up on top and goes in on the bottom, all right? And so it's going to be going in to that loop where the loop is at right now. And so we do a similar kind of thing to what I was doing before, okay? And so we say, okay, so here's maybe, 4 coming in before. And so now let's think about the after. Can someone tell me what's the after going to look like? Is it going to be the same? Is it going to be less lines, more lines? What do you think? It's going to be more. Why is it going to be more? Because it's moving closer to that wire, right? So if you look here at our answers, there was a few people. So we did better than last night, but there's a few people that are saying A, no current. And my guess there is that they're saying, well, the B field is staying constant. But because this loop is moving closer to the wire, okay, afterwards there might be, say, 5 of these going in. Okay, and so what you'd want to do is, again, to combat that, right, to make the after try to look like the before, you want to have a magnetic field coming out, which would lead us to a counterclockwise current. So that one's definitely, I think, harder than the last ones we were doing. All right, so questions on that, anybody? I do agree with the majority there. So those are some examples of Lenz's law. So the way this is going to work out is that we're going to introduce Faraday's law in a second. And generally what we like to do is we use Faraday's law to get a quantitative side of a problem like this. So if we want to get numbers, Okay, so right now we've been talking about directions of currents. And so generally, what we like to do is use lenses to figure out the directions of things, Lenz's law, and then, like I said, use Faraday's law to get more quantitative. So we're going to move on to that here as we go along. We're doing pretty good on this one here. Here's some of your comments from last night. So I think the people who, so as the loop approaches the wire, the amount of magnetic flux traveling through it into the page will increase. So sort of the same explanation we were just saying. This will cause the loop to produce a magnetic field out of the page, necessitating a counterclockwise current. So this person is, again, saying the same thing. So most people, again, they got this right, that their reasoning was pretty good. By moving the wire closer to the current, the magnitude of the magnetic flux is increased. Thus, the current must go counterclockwise. There is no induced current. This is the incorrect because the B field stays constant. So I think that was, again, the people who picked A. So they were sort of saying, well, that B field is going in, so it must be staying constant. But it's a little bit subtler than that because you're moving closer to that wire. So the B field is going to get stronger, which means there are going to be more lines coming in. And there are clockwise using the right-hand rule to check the direction of going outfield. And so I think in this case, they sort of had the direction of it incorrect. Okay. So let's talk about some interesting demonstrations we can show. So we have things called eddy currents, all right? And so in this picture here, we're pulling a sheet of metal through a magnetic field, all right? And so as you can imagine, as you do that, you're changing the magnetic flux through this piece of metal. And you create these whirlpools of current, okay? And so these whirlpools of current, and we call these eddy currents. And just like with Lenz's law, what happens is these currents are going to oppose the magnetic flux through them. And in fact, another way to think about Faraday's law, we talked about this last time, is to sort of frame it a little bit differently and say that in a case like this, what's going on is an induced current is always such that the direction of it is to oppose the motion or change that caused it. Okay, so we talked a little bit about that in terms of that motional EMF. When we moved that bar in the magnetic field, nature, the force that came from that induced current opposed that motion. And so that's what these eddy currents are going to do. If you look at these eddy currents here, okay, you can actually look at, so there's an upwards current going right here. And if you do the right-hand rule, if you take your thumb along with that upwards current, all right, and then put your fingers in the direction of the magnetic field, which would point from the north to the south, the force you get is this way here. So it ends up being a retarding force. And this is a form of magnetic braking. And so that's our first demonstration here. We've got a setup. So we got this machine, electromagnets that create a magnetic field over here. Now it's turned off right now. And so when I drop this piece of metal, okay, it just sort of slides right through, no problem. But then what we do is if we turn on the juice, again, this is, let it get sort of charged up. So this is just basically powering these two magnets. So it's making a pretty strong magnetic field in here. And so let's see what happens. So we can have a lot of fun with this. So it sort of stops like, pretty quick, okay? And again, it's that sort of, that sort of idea. And so now let's do another one here. So here's a thing we can look at. Another example. You may have seen something like this before. Let's look at this one here. So I've got a cylindrical magnet that I'm dropping through a narrow copper pipe. As soon as shown that it's dropped with the North Pole closer to the ground, like in the picture, the tube is at rest. An induced current flows in the direction indicated by the arrow, true or false. So think about this one. This one is, I think, a little bit of a trickier one. So think about this one and see what you think with your neighbors. Okay, so let's go ahead and look at this one. So this is another one where you've got to do some thinking for the magnetic field, okay? And if we remember when we talked about bar magnets, okay, this is not the best picture, but the magnetic field tends to sort of circle around in a fashion such like this, okay? And actually, let me just do this over again. That was how bad that was. So it sort of comes out like this, and it's going to be, in this case, pointing down. It's going to be flowing, and of course, you know that magnetic field lines always connect. So the magnetic field lines are pointing down. And so if I was to draw my picture, my before and after picture of sort of what's going through the top of that copper, all right, maybe initially there's like 2 wires going into it, all right? And what happens is as it gets closer, there'll be more magnetic field lines going into it. Okay, so again, we sort of do the before and after. And so just like before, that means that we want to have a magnetic field coming out, or going up rather, to sort of oppose those, which would lead to this same current that I would sort of call a counterclockwise current. All right? And so this is true for this one here. And what does that mean? Well, that means if we were to sort of draw a picture, okay, so this thing here is making a little bar magnet that looks like it's oriented like that. Okay, because if I take my fingers and circle around that way, the north points up. That's our right-hand rule. Okay, and so what's happening is when I drop that magnet in, all right, you make these eddy currents in there that are sort of making a magnet that opposes what you're doing. And this goes at that other definition of Lenz's law. So the induced current is such to counteract whatever change it is that you're making. And so we got a cool demonstration for that too. So we got a copper pipe. And so maybe we'll do it right over here. And so the first thing, we just got just an ordinary piece of metal, not magnet or anything. And it should come through pretty quick. And now we got the magnet, all right, and this thing, when I drop it in, will sort of take its time. Yeah, anyway, want to go to the bathroom, you can go ahead. It's like I hope it comes out eventually. Yeah, that's really cool, right? And that's probably kind of an expensive magnet. There we go, thanks. And just to be clear, so this piece of copper isn't a magnetic material. So the magnet doesn't stick to it, okay, just when it's not in motion. It's this total idea when you're dropping it down there, you're basically creating a little magnet in the copper that's trying to go against that, okay? All right, so questions on any of that? So again, we got a lot of really cool demos. We had some last time, and we've got some now. We'll have more with this idea of Faraday's law and Lenz. Okay, so Faraday's law. So we've been talking about this, and you'll notice that sometimes when you see Faraday's law, there's a negative sign there. And again, what I think is best for us to do is think about Faraday's law in terms of just like a magnitude. Okay, so we use that to find the answer to the quantitative question that we might be looking for. And then we can use Lenz's law to figure out any sort of direction. So for most of the problems we'll be dealing with, that'll be the way to go. That negative sign is in a sense sort of saying that this EMF is working to oppose the change in the magnetic flux. So it's important to realize that it's there. But I think in practice, it's nicer just to think about this in terms of absolute value. So we had some examples of this in our video. And so let's sort of talk about this. The first thing we can do is we can go back to our emotional EMF example from last time and make that a little bit more quantitative, all right? And so if you remember, so we defined the magnetic flux last time. And so our magnetic flux, the way we defined it, looks something like this here. The magnetic flux is the B field times the area times cosine of theta. And that cosine of theta, that angle is the angle between our area vector, which if you remember was a vector pointing perpendicular to our surface, and the magnetic field. So it's really important to sort of have a handle on what that angle is. That angle theta is in like there. And so here it's b times a cosine of theta. So in this example we did last time of the motional EMF, okay, of this bar sliding down the line, all right, if we set up our magnetic flux, the magnetic flux we're going to get is, so the B field is just the B field, and the area would be the area of this square, or what will soon become a rectangle as the bar moves over. And so what we can do is just call that area L times X. And then in this particular case here, all right, the area vector, we can say, again, is perpendicular to the surface, so it's pointing out at you guys, all right? And so now the thing about this is, because we're neglecting the sign of this, we can be a little bit sloppy. The area vector is in general ill-defined. But in any way you do it, if you have it coming out of the page, then your angle theta is 180, which gives you cosine of -1. If it's going into the page, it's 0, which gives you a cosine of 1. And since we're only looking for the absolute value of the change, it doesn't really matter if we have that extra negative sign in there. And so I'm just going to say cosine theta and use BL times X. And so if we do that, then we got to use some calculus. So d dt of x times lb. And this is where we got to think a little bit. So basically, in most of these problems we're going to be doing on this, and next week when we get some practice and discussion, is we'll be looking at this flux and which parts of these flux are changing. Now, in theory, a number of them can be changing, but you'll find that in a lot of these problems, only one of them is changing. And so here, the length L, right, which the length L is just this length here, of our circuit piece, that's not changing. The magnetic field's not changing. What's changing is this distance x. Okay, and so for us, the derivative, we only have to take the derivative of just that x piece. So it can get more tricky. Okay, you might have to do product rules and stuff, but in most cases, only one of these things. And so dx dt times L times b, and then dx dt is the velocity. Okay, so last time we just sort of said, hey, the EMF in this case is V times L times B, and we sort of thought about it that way, but here we can actually derive that. Okay, so we can actually show from Faraday's law, so sort of another way to kind of get at that. And then just a heads up, so the book and a lot of our problems, they'll be interested in the current, not just the EMF. Right? So like a typical style problem, like on a test, might involve something like this. It would say, okay, find me the current and tell me the direction of the current. So we've been dealing with Lenz's law to find the direction of the current. To actually find the current, you need to find the EMF, okay, the electromotive force, which is basically like the voltage in your wire. So you're sort of creating, again, an EMF in this wire, and so we use Ohm's law to figure out what the actual current would be. So the EMF is our epsilon here, VLB, and we divide by that resistance. And so generally, it's just like sort of one extra step, but it's one of those things where sometimes you're so involved in the problem you can miss that extra step, so just be careful with that. All right, and so let's look here at a quantitative example. So you guys sit down together and think about this with your neighbors. And so here we have a setup. So here's a loop with a magnetic field. We tell you the dimensions of the loop. It's a square loop. And we show you what's happening to the magnetic field. And I want to find the magnitude of the induced EMF around this loop. So let's think about this, and then we'll come back and talk about it. So we'll give you a little bit extra time here to actually, because there's some calculations here, and hopefully get a chance to give this one here a try. looks like we got some good conversations going on here. So let's go ahead and talk about this one. Let's just see what we get. Okay, so there's a little bit of everything. So this is a tricky one. So let's talk about this one. I think, so the good news is I think people who got A, some of this might be just some using ill units. Okay, so let's, again, talk about this. Our magnetic flux here is BA cosine of theta. So again, we're going to make our area vector pointing out so that angle between the area vector and the magnetic field is 0. And so we get B times A for our magnetic flux. And so for me, I'm trying to find my EMF, which is the derivative of this with respect to time. And so in this case, it would be d dt times B times area. So like I said, we got to now decide which one of these is changing. And so for us, the one that's changing is the dB dt. And so to make this quantitative, so now we got to do is look at over here on our curve to figure out just what that dB dt is. And what's nice is it's a nice linear setup, and so basically it'll be the slope of this line here. And so the slope of this dB dt would be, so on the top you're increasing by 0.5 Tesla, and on the bottom you're going over 0.01 seconds. Okay, so that would be how we would set that up. And so in our particular case here then, we've got the 0.50 Tesla over the 0.01 seconds, and then times the area, which would be 0.02 meters squared. And when I did that, I got 2 times 10 to the negative 2 volts. So I think some people, maybe if you put in centimeters, that can be a little bit off there. Okay, so questions on that. So that's an example of how you would do a problem. So we've done two. We did the motion EMF example and one like this here. Questions on this, anybody? Okay. And then just, again, what will typically happen with a problem like this is then they'll, be asking for the current. And so what would happen is they would give you somehow a way to figure out the resistance of that loop. And so you would end up taking that 0.02 volts and divide by whatever the resistance of that loop was. So just remember that, because that's usually generally what these problems will be asking for. So there's an extra little step there. All right, and so if you remember at the beginning of the semester, I showed a bunch of pictures saying, hey, we're going to explain these things. And then here's, I think, one of our last ones. And so here's an electric guitar. So there's a lot of things that work. You've already seen we've got like tons of demos dealing with this particular section. But here's another good example. So electric guitar, you've probably seen these things here. This is the pickup of the electric guitar, right? And if you sort of draw a picture of it, it looks, if you sort of look at these things, it looks sort of like this. It's a little circular thing. So this one's at an angle, right? And it's got, you'll notice, you can see usually little dots here. Those little dots are little magnets, okay? What they do is they magnetize the strings, all right? And so in the region sort of right around that thing, again, that thing is called a pickup. Right around here, it magnetizes the string, and then this pickup, if you actually take one apart, it's got a whole bunch of wires coiled around, okay, a whole bunch of wires coiled around. And so what happens when you pluck the guitar string, okay, you've got a changing magnetic field, right, and so the flux through those coils will be changing, and so those coils get an induced current, all right, that ends up having the same frequency as the plucked guitar string. And so a guitar, electric guitar like this is something that's called a passive device, all right? It doesn't actually need power itself, all right? The signal it creates is from application of Faraday's law, okay? And then you, of course, need something to amplify that signal, but the actual thing itself works based on this principle. Another example, so this picture is a little bit dated, but I can't find a better one. But this is the basics of how a simple microphone might work. Okay, so you have this person singing, and so the sound hits against a diaphragm that's sort of allowed to move a little bit, and of course that diaphragm is a magnet, and you, say, wrap a bunch of wires around that, and as that thing goes back and forth, okay, because of the sound coming onto it, it induces a current. Okay, and that current then again is sent to an amplifier to go on and do what it does. So lots of different applications. An important application that we're going to start talking about now and sort of carry on until next week is an electric generator. So this is a device that transforms mechanical energy into electric energy. And it works on this same sort of idea. So a generator inside a hydroelectric dam uses electromagnetic induction to convert mechanical energy of a spinning turbine into electric energy. And we have a sort of a simple version of this here. Okay, so here we've got, again, some magnets in here, and then we've got two solenoids. And what happens is if I rotate this thing inside this magnetic field, okay, the flux going into these solenoids is going to be changing, and so we're going to create an induced current. And if I get it going good enough, this light bulb here should flash. Is it flashing? Yeah, right? And so this is just exactly the same principle that we generate most of our electricity with, this sort of idea. So again, this is pretty key idea to our civilization right now. So I got a picture, then that's what's, again, inside of these wind turbines that we see, say in the Palm Desert area, right? It's the same sort of idea. You're turning some sort of a looped coil or something like that, a solenoid or something inside a magnetic field to create this induced current and to create our electric energy. And so I wanted then just to look at kind of a simple version of this to kind of give us an idea of where this is coming from. And again, we'll continue this next week, so I'm not sure if we'll get all the way through this. And so here we have a setup, again, a real simple sort of picture. We've got a north and a south magnet. So again, kind of like what we were doing with that generator over there. And we've got a bunch of loops of wire here. And again, the idea is that we're going to turn these loops of wire in this magnetic field mechanically. Okay, I did it by swinging it, but you can do it with the wind. You can do it through steam engines, a lot of different kinds of ways you can go about doing this. Now, one thing I just wanted to mention that we sort of didn't discuss yet, but is important. So we've got this idea of Faraday's law. So our induced EMF is equal, the magnitude of it is equal to the change in the magnetic flux over time. Now, this is for one loop. Now, typically, in most applications, like in that electric guitar, there's a whole bunch of loops, okay? And so there's a whole number of loops. You do that because it can help you get larger EMF and a larger induced current. And so what will happen is a lot of these problems will have a number of N windings. And basically, what you do with that, it's similar to when we had a loop of wire feeling a torque inside a magnetic field. You add in an N. Okay, so if one loop has a certain EMF, then 100 loops will have 100 times that EMF. Okay, so it's sort of an extra thing that we'll add sometimes. And so we have this, again, this loop of wire rotating inside of a magnetic field. And so to do this, again, so we're using this application of Faraday's law. So our plan here is that, Faraday's law tells me that I can get an induced current from this. And so what do I need to do? Well, I need to figure out the magnetic flux for my setup in this particular case. Okay, so again, our equation for magnetic flux looks something kind of like this here. And so what I want to do is set that up for my particular picture. And so so I just wanted to stop just for a second, because I believe this is one of these things that can be tricky for us, this idea of omega as an angular frequency. So you've probably seen this in 2A or at some point, but it's the kind of thing that just comes up periodically, and I think it's really confusing. So I just wanted to talk about it. So here's this sort of picture of, we have a winding, again, some sort of a winding, something that we're rotating with some angular frequency omega. Okay, and so you can think about the edges of that thing as having a velocity v. And so the first time you probably heard about angular frequency was when you did rotational mechanics in 2A, and you can connect the velocity at some point on your rotating stick here, or whatever it is, with this omega. And omega has units of radians per second. Okay, and so another way to kind of think about that is that omega is another way to kind of talk about your frequency. Okay, so when we're doing some kind of rotation, like if I'm rotating this here, okay, we're going to be interested in sort of how many times this thing goes around per second. All right, and that's the frequency, so sort of rotations per second. And so F is something, this frequency that I think most people get. So if this generator is rotating, frequency is the rotations per second. Now, the problem is oftentimes we'll want to put this into a sinusoidal function. And so what happens is it's really nice to write that as a radian. And so here's the relationships. You've probably seen this, the relationship between frequency and angular frequency. And I like to think about it as frequency and angular frequency are really describing the same thing. They're just in different units. All right, so the frequency tells you, rotations per second. The angular frequency tells you the radians per second, which is really giving you the same information in this case, right? But it's just in different units. And what happens is you're going to find that a lot of times we'll put that inside like a sinusoidal function. So we'll put something like omega times t into a sinusoidal function. And so if omega is radians per second, and time would typically be measured in seconds, then what that does is it gives us radians to use inside our sinusoidal function. And so when we're dealing with these sinusoidal functions, which we'll do often, right, it's much nicer for us to be in units of radians, something that the sine function can use. Okay? But that omega itself is really just describing the same thing that frequency does. It's just doing it, like I sort of say, in different units. And then you've also probably seen then, well, typically you might talk about the period. And the period is how much time one full rotation takes for this particular case. And so that's an invert of the frequency f. Okay? Questions on this? Like I said, it's something that typically people don't recall as well when we come to this sort of stuff. So I just wanted to kind of go over it real quick, make sure we're kind of on the same page as much as we can. Okay, so then here's our picture. So here's this picture that I'm basically looking at this thing here from the top down. Okay, so I'm looking at the top down on this one here. And so what we can do is think to ourselves, okay, so I want to somehow describe this in terms of my magnetic flux. Okay, and so we have some magnetic field that's in the picture here, pointing, in this case, that way. And we've got the area of the loop. And so what we want to do is think about that theta. And what's a nice way to do it, you don't have to do it this way. You'll still get the same answers or similar answers in the end, a similar picture, but it just will be a little bit shifted, is to think about starting your loop here. Okay, so at this point, that would be my magnetic field, and then my area vector, which I'll do a different picture, would be pointing something like this here. So I'm going to start it at the point where my magnetic field and area vector are aligned. And then as this thing rotates, okay, if you look at my picture here, it's going to rotate omega times time. And again, that's going to be an angle in radians. Okay, and so we got a picture here, omega times time. And so at some later point, the angle between the B field and the area vector, okay, what I'm calling my theta, is this omega times t. Okay, so in our picture, it starts at 0 and then moves on as some omega times t. And so for our particular example, what we can do is write this flux out in a sense like this. And so say that our magnetic flux is B times A, and then write it as cosine of omega times t. Like I said, I think typically people have issues with this. So let's stop there, and then what you can do is on the PCQ for Monday, you can send me other questions about that. But we'll pick this up then and carry on next week. Thanks, guys. We'll see you later.